The universe speaks in many languages. We see it in the swirling colors of a nebula, hear it in the crashing waves of an ocean, and feel it in the gentle warmth of the sun. But there's another language, one hidden within the heart of our machines, the language of computational complexity. Imagine a world where computers could only understand a few simple instructions. This world, my friends, would be a very different place. We rely on computers to solve complex problems, from predicting the weather to mapping the human genome. But how do we know if our solutions are actually efficient? This is where computational complexity comes in. It's the study of how much time, memory, or other resources an algorithm needs to solve a problem. Think of it as the efficiency rating of your favorite appliance. But instead of energy consumption, we're measuring how well an algorithm uses computational resources. Just as a chef carefully selects ingredients for a recipe, computer scientists use complexity analysis to choose the right algorithms for the job. By understanding complexity, we can write programs that are not only correct but also elegant, efficient, and capable of tackling the universe's greatest challenges. In the digital realm, efficiency is not a luxury. It's a necessity. Every click, every swipe, every computation requires time and resources. And as we delve deeper into the world of big data and artificial intelligence, the need for efficient algorithms becomes paramount. Think of it like this. Imagine you have to find a single grain of sand on a beach. You could start at one end and meticulously examine each grain one by one. This approach, while guaranteed to find the grain eventually, would be incredibly time-consuming. A more efficient approach would be to divide the beach into sections, then subsections, and so on, eliminating large areas with each step. This is the essence of algorithmic efficiency, finding clever ways to break down problems and arrive at solutions faster. Computational complexity provides a framework for analyzing and comparing the efficiency of different algorithms. It allows us to quantify how the performance of an algorithm scales with the size of the input. Just as a telescope helps us see distant stars, complexity analysis allows us to peer into the heart of an algorithm and understand its true nature. Let's imagine two intrepid explorers, each tasked with mapping a vast and uncharted territory. One explorer, armed with a compass and a trusty map, sets off on foot, meticulously charting every hill and valley. The other explorer, equipped with a hot air balloon and a keen eye for patterns, takes to the skies. From their vantage point, they can quickly identify major landmarks and sketch out a rough map of the entire region. Both explorers will eventually complete their task, but the one with the aerial perspective will finish much faster. This analogy highlights the difference between algorithms with different complexities. Some algorithms, like the explorer on foot, take small incremental steps, their execution time increasing linearly with the size of the input. Others, like the explorer in the balloon, leverage clever techniques to solve problems exponentially faster. By understanding these differences in complexity, we can choose the right tool for the job, whether it's sorting a list of names, finding the shortest route on a map, or simulating the evolution of the cosmos. Time, as we perceive it, is a relentless march forward. But in the digital world, time can be measured in the blink of an eye, in nanoseconds fleeting faster than a hummingbird's wings. And it's in these infinitesimal slivers of time that algorithms come to life. Time complexity, the timekeeper of the algorithm world, tells us how the execution time of an algorithm grows as the input size increases. Some algorithms, like diligently searching through a phone book page by page, exhibit linear time complexity, double the input, double the time. Others, like searching a sorted phone book by repeatedly dividing the search space in half, boast logarithmic time complexity, double the input, add a constant amount of time. And then there are the behemoths, the algorithms with exponential time complexity, where even small increases in input size can lead to astronomical increases in execution time. Understanding time complexity is crucial for designing algorithms that can handle the ever-growing data sets of our digital age. It's the difference between waiting minutes, hours, or even years for a program to finish. Space, the final frontier for algorithms. In the boundless expanse of space, celestial objects dance and collide, their movements governed by the invisible hand of gravity. In the digital cosmos, algorithms operate in a similar realm, their performance constrained by the availability of memory and storage space. Space complexity, the cosmic cartographer of the algorithm world, measures how much memory an algorithm needs to run. Just as a spaceship requires fuel to journey through the cosmos, algorithms need memory to store data and perform calculations. Some algorithms, like adding up a list of numbers, require a fixed amount of memory regardless of the input size. Others, like storing a massive database of astronomical observations, demand space that grows proportionally to the input. As we venture further into the realm of big data and machine learning, space complexity becomes increasingly important. It's the difference between an algorithm that fits comfortably on your laptop and one that requires the processing power of a supercomputer. The art of choosing the right algorithm. Imagine you're a chef, standing in a kitchen stocked with every ingredient imaginable. You're tasked to create a culinary masterpiece. But with so many options, where do you even begin? The same dilemma faces computer scientists when choosing the right algorithm for a problem. There are countless algorithms, each with strengths and weaknesses, and selecting the optimal one is both an art and a science. This is where our understanding of computational complexity becomes invaluable. By analyzing the time and space complexity of different algorithms, we can make informed decisions about which one is best suited for a particular task. Just as a seasoned chef knows which spices complement each other, a skilled programmer can navigate the world of algorithms, selecting the perfect one for the job, whether it's sorting a database, finding the shortest path, or simulating the human brain. Real-world complexity, from Google Maps to Netflix. Computational complexity is not some abstract concept confined to the halls of academia. It's woven into the fabric of our digital lives, powering the apps and services we use every day. Take Google Maps, for example. When you ask for directions, Google's algorithms spring into action, calculating the shortest route from millions of possibilities, taking into account traffic conditions, road closures, and even your preferred mode of transportation. Or consider Netflix, where recommendation algorithms analyze your viewing history and compare it to millions of other users to suggest movies and shows you might enjoy. These algorithms are constantly learning and evolving, striving to provide the most accurate and personalized recommendations possible. From social media feeds to online shopping, computational complexity plays a silent but crucial role in shaping our digital experiences. It's the invisible hand that guides us to the information we seek, connects us with friends and family, and entertains us with personalized content. The never-ending quest for faster algorithms. In the world of algorithms, there's a saying, good, fast, cheap, pick two. We can have algorithms that are fast and efficient, but they might require significant resources. Or we can have algorithms that are simple and easy to understand, but they might be slow and inefficient. The quest for faster, more efficient algorithms is a never-ending pursuit. Computer scientists are constantly pushing the boundaries of what's possible, developing new algorithms and refining existing ones to squeeze every ounce of performance out of our machines. One area of active research is quantum computing, which leverages the principles of quantum mechanics to perform computations that are impossible for classical computers. Quantum algorithms have the potential to revolutionize fields like medicine, materials science, and artificial intelligence. The search for faster algorithms is a testament to human ingenuity. It's a reminder that even in the digital realm, there are always new frontiers to explore, new challenges to overcome, and new discoveries to be made. Unlocking the future complexity and beyond. As we stand at the precipice of a new technological era, our ability to understand and harness the power of algorithms will shape the future of humanity. Computational complexity, the silent language of computers, will play a pivotal role in this journey. By understanding the principles of complexity, we can design algorithms that are not only efficient but also ethical, fair, and unbiased. We can create artificial intelligence that augments human capabilities, solves our greatest challenges, and unlocks a future filled with wonder and possibility. The journey into the world of computational complexity is a journey into the heart of computation itself. It's a journey that takes us from the smallest transistors to the largest supercomputers, from the mundane to the profound. And it's a journey that reminds us that even in a world dominated by technology, it's our human ingenuity and creativity that will ultimately determine our destiny. If you learned something new like the video, share your thoughts in comment section and don't forget to subscribe the channel for more related videos.